So what we had last time was we defined this thing called the exterior derivative, which took k forms to k plus 1 forms. So remember what that means is you're basically adding another dx that you're wedging with. Sorry. And it has various properties, some of which are obvious, some of which are not. So if omega and eta are both k forms, then you take their sum, and d of the sum is the sum of the b's. That's easy. If you have a function, and you take omega and multiply it by a function, and you have the baby case of the product rule, which is to differentiate the function wedged with omega and add f times d omega. So this is a k plus 1 form. Omega is a k form. This is a k plus 1 form because you're taking df, which is a 1 form, wedging it with a k form, and that's a k plus 1 form. And more generally, if omega is a k form, and I don't remember what letter I used, phi is an L form, then you can say that the derivative of omega wedge phi is derivative of omega wedge phi, plus there's this funny minus sign that shows up that you need to be careful about, omega wedge d phi. So the way I like to remember this is that you think that to move the d across the omega to get it to the phi is like having to do a switch so the minus 1 to the k shows up. There's no L, but there's a minus 1 to the k that shows up. And then the last rule that we had was that if you take d of d omega, you always get 0. So I am going to prove these two. But before I do that, since you have web work that requires another concept, I want to talk about the other concept and do some examples. And so eventually we'll have proofs of everything. So you all learned way back in calculus I've reminded you of this before, that you can do integration by substitution. Remember that? So you had something like the integral from a to b of f of u du, not from a to b, I'm going to change that, is the integral from a to b of f of g of x, g prime of x, dx, where now this is going from g of a to g of b. You guys remember you could do a substitution? You usually think of it on this side, right? That you think, oh, if I let u equal g of x, this becomes du. So what you're actually thinking of doing here is having a 1 form you're actually thinking of taking the function g, which maps the interval a, b to r. And what you're actually doing here is saying, gee, if I take the 1 form that lives on r, and I pull it back, I substitute u equals g of x, then there's going to be what I'm about to define, what's called the pullback. So this is trying to motivate what I'm about to do. You get a pullback of a differential form that lives here, back to a differential form that lives here. So you get what's called the pullback of omega. And the way the pullback works, I'm about to tell you, is the function, you replace u with g of x. So u is your variable here. You say u is g of x. So f of u becomes f of g of x. And then you pull back du. And the way you pull back du is you say to yourself, u is g of x. So what's du? For what we've been doing the last few days.
G prime of x dx.
It's the derivative, it becomes dg. Which we now know how to do. You've been doing this for at least a day now. We only have one variable, so you don't have to write down a partial respect to x1 dx1 plus a partial respect to x2 dx2. You just write down derivative with respect to x dx, because there's only one variable. And so presto magic, pulling back the one form omega gives you f of g of x, g prime of x dx. And then the magic is, well, integral of the pullback of omega, which is this one, is the same as the integral of omega.
And will that be true in general?
And that's going to be true in general. And that's going to be the change of variables theorem, ultimately in general. So I'm trying to motivate, though, this idea that you learned in Calc 2, where you just say, make a substitution, formally plug in u, g of x there, formally plug in du as g prime of x dx, which you were trained to do in calculus, even though those things didn't mean anything to you. Mm-hmm.
What is the operation that we're doing to the limits of the integral in terms of...
Well, so I'll talk more about that when we do integrals next week. But what's literally going on here is when you take this function g, it's literally mapping from the interval a, b to that interval. It's not mapping to all of r. The image. So remember when we had the change of variables theorem, one side was an integral over omega, and the other side was the integral over g of omega. That's exactly what's here. This is the integral over omega, and this is g of omega. Mm-hmm.
So historically, did people do what we did first, just like a formal substitution, and then figured out this theory?
Yeah, differential forms came way late. Differential forms came around the turn of the 20th century.
But this is sort of the rigorization
of this
what
notational
was just
procedure
known as
that people were doing, right? I mean, going back to Leibniz and Newton, people thought about differentials in terms of small changes. The differential forms viewpoint came centuries later. Okay, so I want to define this pullback process officially. So here's the official definition of pullback. So the basic plan here is that you have a function that maps, say, some open subset in Rn, or maybe, I don't know, it doesn't matter, Rk, say. No, I don't want it to be K. Rn, and it maps to some other dimension. It doesn't have to be the same dimension. And G is smooth, of course. And I'm going to start with defining, let's say variables here are u's. This is like what we've been doing earlier in the course. Variables here are x's. So officially, we're going to have u1 to un as our variables in our n. And then you're going to have x, which is given by m different component functions Right, we're mapping to Rm, so that means it's a vector valued function with m components, each of which is a function of u. And those, so you're giving x, if you like, x1 to xm, as functions g1 to gm of your variable u. So going to write down the definition officially, and then we'll do a bunch more examples. So what I want to do is define what's called the pullback, which takes k-forms on Rm, or let me even say g of u here, if you want, and pulls them back to k-forms on u.
So it's changing.
Yeah, I'm not sure I want to do that. Let me just put Rm here.
So it's changing sort of the domain of the k-form?
Yes.
Okay.
So it's going to give you a way with a k-form here to pull it back and have a k-form here.
Okay.
And the process is going to be what I did for you here that you've been doing without thinking. You're just going to substitute everything that had to do with x's and dx's here. You're going to substitute in terms of u's.
Is n less than n?
Doesn't have to be. That's why I gave up on what I was putting there. No relation needed between n and m. Might be equal, n might be bigger, n might be smaller. So we can do examples of all of those. Okay, here's the rule. The way you pull back a function if you have a function, a regular plain old smooth function, how do you get a function here and turn it into a function here? You've been doing this for years. You have a function here, how do you make it start back here instead?
Just limit it to u.
What do you mean?
The inverse?
No. No, I'm not doing derivative, I'm just saying how do you...
Oh, well, you can take its magnitude.
No, what? I have a function
Oh,
here.
sorry,
I
yeah.
have a function mapping here. And I have a function g that goes here. How do I get a function from here to here?
Composition compose.
Fog. Compose functions. That's what we did here, folks. Where we had f of u, we put in u as g of x, and we had fog. All right? Second list on the rule. How do you pull back a dx sub I? Little I, not capital I. By definition, if I want to pull back dx sub 1, I just take the derivative of the function g sub 1. If I want to pull back x sub 2, I just take the derivative of g sub 2. So this is just dg sub I. And you say to yourself, I don't remember what that means. Well, what's d of a function?
Did you say a vector over D?
No, this is the ith component function.
Okay.
So this just means take the partials of the ith component function with respect to the various variables times d of the respective variable. This is what you've been doing if you did your web work. This is what you've been doing. Okay? Well, how do I pull back dx sub capital I's? How do I pull back a k thingy? A k differential form. I'm going to say g star of a wedge product is the pullback of the wedges wedged. Pullback of the forms wedged. So pullback, the way math people say this is, pulling back commutes with wedging. Wedging and pulling back is the same as pulling back and then wedging. So if you know how to pull back one forms, you know how to pull back anything because you can build, well, I lied, I need something else. G pullback of a sum is the sum of pullbacks, so it has to also be linear. So omega plus eta is pullback. So let's just do some examples.
So is pullback some sort of weird quote-unquote linear map over forms?
Yeah, it is linear, but it actually is compatible with the wedge product structure as well. So it's actually an algebra homomorphism, whatever that means. And it's also linear over smooth functions, in the sense that pulling back a function times something, if you put in the composition, is a pullback of the function times pullback of what you have. Okay, let's do examples. So, for example, suppose I took G mapping one dimension to 2 dimensions. You can probably guess what I'm going to write down for G.
Cosine sine.
How about cosine sine? So I'm parameterizing a cycle. But I want to take a one form on R2 and pull it back. So for reasons unknown to you at the moment, I'm going to consider the one form so this is a one form on R2 minus the origin. Some of you have been seeing this in your web work nightmares.
Just making sure, R, it has to be R2 though, like the, what
What do
the
you mean
map
has to be?
to,
No, I could take a curve in any Rn I wanted.
but with the element of, with,
Or this has to be there.
what those, they do or they don't?
Yes.
Alright,
So the parameterized curve is mapping me into the set where my one form is defined. So this curve didn't hit the origin, so let's say it's mapping to R2 minus the origin to help me with that. All right, how do I pull back of omega? And some of you have seen this omega somewhere. And web work. Well, what's the rule? Well, I have a function here, and I have a function here, and I have a function here. How do I pull those back?
Composition.
No, I'm not doing dx and dy yet. How do I pull back y? How do I pull back x squared plus y squared? I just plug in, I compose, right? So this is going to be, first of all, what's x squared plus y squared? 1. Okay, now I have to pull back negative y. Well, negative sine t. Now how do I pull back dx? So pullback of dx, remember, means, well, dx is the first, x stands for the first component here. And y is the second component. So I just do d of what? Cosine t. Which is? Keep going. dt. Negative sine t times dt. I need a longer fraction sign. Pull back x.
Cosine t. Cosine t.
Hmm?
Would it be cosine t?
Sine
Cosine t. And then what's the pullback of dy?
Cosine t dt.
Drum roll. What do we have? Times dt. So that weird looking one form turns into something totally innocent when I pull it back to the interval that parameterizes the circle.
So this would be the analog of a nice change of variables.
If you were working on the circle. This is the
Yeah.
parametric, so where you see where we're headed is, this is a way of thinking about the one manifold, the circle, parametrically. So if I say hypothetically next Monday or Tuesday wanted to do an integral of hypothetically a one form over that circle, over that one-dimensional manifold, I would parameterize it, I would pull back, and I would do the integral. That's where we're headed. All right, let's do some more examples. Now, Ken actually asked if we could take a mapping from a bigger to a smaller. So suppose you actually mapped G from R3 to R2. Anybody want to give me a mapping from R3 to R2? Projection. So you want me to take G of U1, U2, U3 equals
U1, U2.
U1, U2? Sort of boring. Okay. What would you get if you pulled back? So let's see. So do you want to do a one form on R2 or a two form on R2 or both? Both. All right, we'll do both. So let's do omega in a one that's a one form, and let's do phi that's a two form. So you guys make up an omega and a phi and give it to me. Give me a one form on R2. Don't be ridiculous, but make up a one form on R2.
Dx plus y dy.
Okay. Somebody give me a two form on R2.
X, Y, dx,
So now how are we going to pull back omega?
plug it in.
So how do you pull back dx? Well, here's x du u1 plus sort of boring, isn't it? What's the pullback of phi?
U. Du,
Okay, so it wasn't so interesting. But what's going on? These things have no U3s in them. Well, duh. Because when you pull back something that's on the U1, U2 plane, you're not going to have any variable coming from the third direction. It disappeared when you projected, so it's not going to reappear when you pull back. So that was not so interesting. Let's do it the other way.
U2, U1.
Let's go from 2 to 3. So geometrically, what am I thinking of if I map two variables to 3?
Adding a third dimension.
Cross.
Function of from two variables to three variables.
Surface.
It's a parametric surface. That's what you're thinking about, right? If you can move around in R3 with 2 degrees of freedom, that's like having a surface. Effectively, this would be a parameterization, say, of a piece of a two-dimensional manifold, for example. All right, anybody have a favorite? So at this point, to avoid subscripts, I'm just going to write U and V rather than U1 and U2. We could do a sphere. You want me to do the sphere? Then in spherical coordinates, right, would be the natural way to parameterize it.
Whatever.
Or we could do,
Helix sounds fun.
well, not a helix,
A helicoid.
helicoid. Okay, there's a helicoid. So we actually did this example last Friday, right? Is that right? It's one of our examples. All right. Now, what would happen if I took a 3 form on R3? What would be true about the pullback?
That would also be a 3 form.
It would have to be a 3 form. on R2.
So it would be 0?
So it has to be 0. Jackson, you want to explain?
You'd have to repeat a coordinate, like a D, you'd have either 2 DUs or 2 DVs wedged.
Right, when you pull back, so we're going to compute this. If you pull back dx, dy, or dz, it's going to involve du's and dv's. When you wedge 3 of them together, you have no choice but to get either 3 du's wedged together, 2 du's and a dv, 1 du and 2 dv's, or 3 dv's. But anytime you wedge d something with itself, it's 0, right? Because you concatenate your indices and you don't repeat it. So if you actually were given a free-form, you shouldn't spend an hour computing. You should just stop and think, how I would have to have a free-form on R2 and there aren't any other than 0. All right, let's do something more interesting. Let's pull back, let's say,
So is that only for 3 forms on R2? Or is that, can we expand this like it's only
4
0?
forms on R3.
Yeah, so anytime it's 1 bigger,
it doesn't have to be 1.
Anytime.
Anytime this is bigger than that dimension,
0.
you have no choice to have 0. Agree, Jonathan? Okay. So let's pull back z dx plus x dy minus y dz. I just made that up. It doesn't. You'll see next week what these things mean in terms of physics. So maybe Michael will be interested. I don't know about the rest of you, but let's just pull back and what do we get? Can you just
3
let's do this.
negative v sine
Cosine u dv
Next to v sine.
minus v sine u du. Does everybody agree?
So are we just, what are we differentiating perspective?
Everything. Remember, d of a function is the sum of the partials times corresponding d thingies. So you do the complete derivative. Plus x dy pulls back. 3. dy.
Negative.
Sine u dv.
plus v cosine u
Okay. And then the last term is minus y. Pull back of dz. 3du. And you could collect terms and write it as something or other du plus something other dv, but it's going to be sort of yucky. But you could do it, right? So you could say it's blah du plus blah dv.
Is that like the bold test?
So having done this, will this allow us to calculate like flux intervals across a helicoid?
That was the end of your sentence?
Fluxes across the helicoid?
Sure. Oriented surfaces. Yeah.
Okay.
That's where we're headed. Now, suppose I asked you, what's the pullback of, say, z dx wedge dy? What would it be?
so
So you have the z.
I have z, it just pulls back to 3u. Now, how do I pull back dx wedge dy?
You have to use a
Write
rule.
down
It's
dx.
So you pull back dx. Have we already done that?
Yeah. Cosine u dv minus v sine u.
This is the pullback of dx. Have we already pulled back dy? Do I have to recompute those? No. Just have to wedge them. Now we'll see if you guys remember something from a couple days ago. What happens when I wedge these together?
Only 2 times that.
So I have a let's think about a monster FOIL exercise here. So you have a du, wedge a du term.
Zero.
I have a du, wedge a dv term. Not zero, so what do I get? Du, wedge dv.
Or could you do dv du just get rid of minus?
We could. Now what happens with the dv stuff? All right, that was smart, Ted. Get another piece of green. That was not what I meant to do. dv wedge dv.
Zero. Yeah.
dv wedge du.
Not.
Not zero. So I get plus v cosine squared u dv wedge du.
Yeah, I would want to switch the du dv won't.
Now, if you wanted to get in terms of the standard order back here, which you might want to train yourself to do for future reasons, you might want to put it all in terms of du's and dv's. I mean, du wedge dv's. So I would switch this one and get a negative. So I would get negative v du wedge dv. Now, what did we actually just do with this computation?
Negative 2v?
Say what?
Won't it be negative 2v?
No. Cosine squared plus sine squared.
Yeah, but you have a negative v, and then you would have another negative v when you switch it.
Pull out the negative.
You're not adding them, you're
Oh.
pulling out like factor.
Yeah, so a negative becomes.
I know. I know.
Perhaps the video expert will edit that bit out. Okay. What just happened with that calculation? Look, folks, we had dx, dy, dz that we pulled back. Those have du and dv slots, and the coefficients are partials. In other words, we've got the derivative matrix for dg. And very coincidentally, that derivative matrix looks a lot like what we've just been doing. What am I doing?
Thanks. Yeah, I think you.
Is that better?
Yeah.
There's the derivative matrix. And the partials with respect to u are here, if I didn't do it wrong. And the partials with respect to v are here, if I didn't do it wrong. So in other words, the first column is sort of a placeholder for the du coefficients. And the right column is the placeholder for the dv coefficients. Make sense? What did you do when you pulled back dx and you pulled back dy and you wedged them? In terms of this matrix, what did we do?
Took the determinant,
Of?
the top two lines.
There you go. So when you pull back dx wedge dy, you're getting the determinant of that piece of the matrix times du wedge dv. If I had pulled back dy wedge dz, I'd be doing this cofactor, this minor of the matrix.
Why is that?
Well, that was what we observed the other day. That the wedge product is building in determinants everywhere you look. Right? I mean, you're getting this du plus this dv, wedge, this du plus this dv, and because of skew commutativity, you end up with this term with a plus, this term with a minus, and the other terms disappear. So the pullback of dx wedge dy is the determinant of the partial of g1 with respect to u, partial of g1 with respect to v, partial of g1, g2 with respect to u, partial of g2 with respect to v, du wedge dv. So you're taking the appropriate rows of dg, taking the determinant,
Not always use square.
etc. If you have a 2 form, it's going to pull back to a 2 form. So you have to take a 2 by 2 submatrix no matter what the dimensions of this thing are.
Oh, it's a one form.
If you had more of the 2 forms here, if we had more variables and you had du1 which du2 and du3 which du4 and so forth, you would be doing appropriate blocks of the matrix, but it's always going to be a square determinant that you're doing as the coefficient. Magical stuff.
Why does it always end up square?
Because you're pulling back a 2 to a 2, going through the same thing.
So you're going to have 2 rows determined by which DCs you're wedging here, and the columns you're using are depending on which coefficients we're looking for. So in general, you would take the pullback of dx sub capital I, if the length of capital I is k. This is going to be a sum of basis k forms in the u variables, where the length of j is also k. And I'm actually going to say j increasing here, so it's a basis. And what goes here as the coefficients is the determinant of the square matrix you get by using the I rows and the j columns. So I'm going to call that the matrix dg sub I, using those rows with respect to u sub j. And there are k of these and k of these, and you get the sum of those. Best thing to do is do examples and see what's going on. You will convince yourselves very quickly. All right. Well, just for funsies,
I thought we only played for keeps.
let's go back to this example that we did here, just above.
To number 3.
I wasn't numbering them. Well, yeah.
Oh.
This. You're right, I had 3. Let's do this example here. Dagger.
Whoa! It's not the birthday anymore.
No, it's been gone for ages.
Yeah.
Yeah.
Get it tired.
So back to example dagger. We had the pullback of this 1 form omega, which I won't write out again at the moment, was some mess of du's and dv's. Well, I'm actually going to collect terms for the moment. How many du's have I got? I've got minus 3uv sine u plus v squared cosine squared u. Following me? Minus 3v sine u, all du. I'm just collecting terms. Plus, how many dv's? 3u cosine u plus v cosine u sine u dv. Is that correct? Is somebody checking me? And just for fun, I'm going to ask you half the room to do one thing and the other half of the room to do another thing. Okay. People on this side. Side 1.
Yeah, what? We're definitely side 1. First the worst, second's the best.
Side left.
Pretty much so we want to-
Side right.
So it's you
right now. All right, left.
Whoa, 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 whoa.
Which one's
Christ,
stage,
like,
too?
you're looking at a planar mirror.
I don't know. I think we're on the stage right now.
So why do you think it's the fucking first?
Side like Bravo Charlie.
Let's see.
Side
If I do this by politics, which one's L and which one's R?
We have Davis, so we're definitely R.
There's maybe another.
Yeah, I think that might be right. All right. So side R, you guys are going to compute for me d of the pullback that we just wrote down. and simplify it. You guys, side L, I want you to compute d of omega. One side gets to work harder than the other, I hate to break it to you. And then I want you to pull it back.
What? Oh, 5 steps.
I trust you guys to get more work done, except for Cameron.
Hey.
Wait, really?
We're probably over there working on a challenge problem.
We're there to get more work done?
So, you guys take d of this thing and simplify it. You guys first compute d omega. I'm now wishing we had done a slightly easier example, but it's all right. We've got 23 minutes left. Well, get to work!
23 is
Here's
interesting.
omega.
5.
So what's d of it?
I forgot how to take the easy off.
And very conveniently for you, I've left the matrix sitting here, so you should be able to do this very easily. So in fact, the work's about tied.
Just
Wait, there's the product rule. Come on, man.
I lied. You guys have the easier ones. Do it.
I want answers.
You have to wait like an hour.
5?
You have web work like this, by the way.
Yeah.
We have hours to do web work.
You don't need to. No, we don't. Because it's already to do less with the U at the end, so you don't think that the U of those terms. Those are the
I should offer free pizza to the team that wins first or something.
Oh, then I'm going faster.
Anything for pizza.
And
You
should,
do
not
anything for
am.
pizza. This makes
It's
sense.
not in my power to do it today.
And do free t-shirts, that's how you get people to do
All right, come on, guys. You should be done. I'm the team L. And team R, where you're just sitting
3U
there.
cosine U? Is that what that is?
U cosine U. Yes. Why are people just sitting?
Because we expect everyone else to do it.
Seriously, work. All of you.
I vote we make Cameron do all the work.
Yeah, you. If your grade's riding on that, you really want to do that?
Hey. I don't need
Is
it.
that cosine U sine U again?
Yes, this class is not
Is it-
required. I'm not sure
I
how to
would
do
answer
this.
side or
DUs and DBs.
V cosine U sine U. Yes, that's what it is.
for side R, should 3U sine U minus B sine U cosine U minus
Wait. 3U sine U. Wait a minute.
minus
Go on.
V sine U cosine U minus 2V cosine squared U.
Is that everything?
Yeah,
Is that correct?
I don't know. So we got D.
Well, you got a team here.
Team's still working.
Well, team better come to a consensus. What about other team?
Oh, 3 sine U cosine. No, this one 3 sine U plus 3 cosine E minus.
Wait. Is this term right?
Taking our respect to D. Where's the negative go?
The negative went away when you switched the order to du wedge dv. So this term belongs there. Then I should get a 2v cosine squared u,
And then change to negative.
which becomes negative. And then presumably I'm getting another one of those from the product rule here. And then this one is giving me a minus 3 sine u. Where did that go?
It cancels.
It canceled. Becomes a plus 3 sine u. And then when I do the product rule here, I'll get a minus 3.
Did you cancel?
Fine,
No, that's not canceling.
No, no.
Patrick, you're wrong.
I have an answer, but nothing canceled at all.
Well, I'm putting a plus 3 sine u here, and then I'm putting
I think I
a
have the wrong answers.
sine u. Root of this with respect to u, I'm going to get a 3u, negative 3u sine u.
I got two.
I don't know where
These cancel, don't they?
I think it's just.
Yeah,
Okay, but I think the first was actually.
Wasn't this fun?
Because you take the.
It's what, it's the top and the bottom, not the.
Right, but you take the bottom first.
Okay, we got
Yeah, we got it. We agree.
we got 3u sine u minus 2b cosine squared u plus 3 sine u plus 3 cosine u minus 3u sine u.
Which cancels.
Which cancels this.
Right.
Okay.
What about this term?
Minus v sine squared u.
3 cosine u minus b.
We didn't have a term like that.
We have a term like that. We had
minus 3 sine.
plus v cosine. You forgot to do the product rule on that one. The product rule is not that, right?
So I have to take the u derivative
Right,
here.
so it becomes v cosine squared u minus v sine squared u.
I did.
Okay.
Patrick, you're fired.
And that's how we do it. In the
All right,
freshman class.
Team L.
We don't really know what we're doing, but we got
about
3 cosine u minus v minus 3 sine u, and then that's du which dv.
What do we get minus v?
Oh, I got minus v.
Well, I'm going to break the news to you guys, since it's time for us to be done.
We're both wrong.
These are supposed to be the same.
So,
Well, maybe there's trig
So that-
identities.
That is a great property that we are going to do on Monday to add to our list of properties here. That D commutes with pullback. If you pull back and take D, you get the same thing as first taking D and then pulling back.
Yeah, that's a trig
They don't
identity.
look the
It's
same on Webword.
There's a trig identity there.
This is
Cosine
cosine
squared
2u.
Like it's gonna take some
Yeah,
work.
that's 1. Or no, it's
No.
not 1. It's gotta work out.
All right, well,
so when do we get our pizza?
So,